Here, we have the same table, but more proper one. So we can read the table and make inferences. Let me keep track with my pointer. What we're gonna do is, start from the end, and make inferences in each node. Okay. Let's start with the upper path. Who is the last person? Here, Talia decides last, so we'll start with Talia. In that case, we assume that Emily contributed, Nina also contributed. And the question is, what would Talia do? On the right, you can see the scores. Let me write it again to see it clearly. This column is for Emily, middle one is for Nina, and last one is for Talia. With this information, we can say that, if Talia contributes she gets 3 points, and if she does not contribute, she gets 4 points. We assume each player will act logically. So, in this case Talia wouldn't contribute, she would choose this way. So we can eliminate this outcome. Okay, let's continue with this node. Emily contributed. Nina didn't. What would Talia do? Of course, she would choose the upper way. Because she wants to get 3 instead of 2. Thus, we can eliminate this outcome as well. So here, we can eliminate this one. Because Talia would choose contributing. Then finally, we can eliminate this one since Talia will choose not to contribute. Alright, we are done with Talia's decisions. With these information, we can now make assumptions for Nina's actions. The amount of possible outcomes is decreased to 4 from 8. We'll not consider the eliminated ones anymore. You might now understand what we are trying to do here. We are trying to eliminate the dominated paths to reach the equilibrium. This is so-called rollback equilibrium, because our method was starting from the end, for rolling back to beginning. If things are clear so far, that's perfect. Let's just continue with Nina. We will clarify Nina's action by assuming Emily's action. If Emily contributes, in this node, we know that Talia's action depends on Nina's action. What I mean is, if Nina contributes, Talia will not. If Nina doesn't contribute, Talia will contribute. So, we have 2 options to consider. In this one, Nina gets 3 points. But, in this outcome she gets 4 points. Again, we assume Nina's action will be logical, so that she will choose the second one. Hereby, we can eliminate one more outcome. Okay. Let's do the same thing for the second subtree. Here, what do you think Nina will do? Stop the video here and think about it. She would choose to contribute to get 3 points instead of 2. So, we can eliminate this one as well. Nice. Finally we left with only 2 options. With the information of Nina and Talia's action, now we can comment on Emily's action. Remember, the game is sequential and Emily knows this table as well. So, she can make the same method as we are doing now, before deciding. As a result, Emily will think like this. If I will contribute, this will be the outcome and I'll get 3 points in the end. If I won't contribute, this will be the outcome and I'll get 4 points. She will choose not to contribute. So we can now finally eliminate this one, and left with only one outcome. You can call this one as optimal solution, or equilibrium path of the game. So, what are the results? First of all, we can say that Emily will not contribute. Also, what is the equilibrium? By the way, generally speaking, equilibrium mostly means the optimal strategy for all players. Let's write the equilibrium path. The equilibrium path basically tells us the way that goes to the equilibrium. Then, the equilibrium path is DCC. D for Emily, C for Nina, and again, C for Talia. Be careful here, only Emily gets 4 points while others get 3. Why is that? Because Emily decides first. This game was a good example to see the first player's advantage in sequential games. But don't forget, that doesn't mean that, in every sequential game the first player has the advantage. No, it doesn't mean that. Sometimes it's better to be the second player. We'll see other types of sequential games in the future, but in this example, being the first player is advantageous.